Happy learning! Today we're going to talk about higher order derivatives. So the derivative of a function, right, if you found f prime of x, what you get is a function. So we could take its derivative. And so that's what we're going to be doing today. We're going to be taking derivatives of derivatives. So the derivative of the first derivative is called, the derivative of the first derivative is called the second derivative. All right, so what do we use for notation for the second derivative? We write y double prime, or f double prime of x, or d squared y over dx squared, or d squared over dx squared f of x. All right, this is saying two derivatives, right? Two primes means two derivatives. These are all just different ways that you'll see the second derivative. All right, so let's find y double prime. If y is equal to 3x to the third minus 4x squared plus 5. All right, so pause the video, try this on your own. It's really straightforward, right? You take the derivative and then you take the derivative again. Welcome back from the pause. All right, so we want to find y double prime. And so let's just start by finding y prime. And we look at our function. What rules do we have to use to take the derivative of this function? Just the power rule, right? There's no products here. There's no quotients. There's no composition of functions. It's just a regular old polynomial. So let's use the power rule. And so what do? We bring the power in front. 9x squared minus 8x. The derivative of 5 is 0. That's y prime, but we want y double prime. So we need to take the derivative of this. Bring the power in front. 18x minus 8. There you have it. That's the second derivative of our function. Let's look at another one. Again, we'll find y double prime. If y equals the square root of 2x minus 1. All right, so this one's a little bit trickier, right? We have this square root. How do we deal with the square root? Okay, so look back to some old videos to see how do we deal with the square root. But I'll show you right now. We're going to rewrite the square root as 2x minus 1 to the 1/2. And now we could take the derivative using the power and the chain rule, right? We have some function raised to a power, so that's power and chain. Bring the power in front. Keep the inside the same. Subtract 1 from the power. And boom, we need the chain rule. All right, so we got to remember the chain rule. That's why I tried to scare you there with the boom. All right, so we bring the power in front. Keep the inside the same. Subtract 1 from the power. Chain rule. All right? 2 times 1/2 is just 1. So this is 2x minus 1 to the negative 1/2. That's our first derivative. When you're taking multiple derivatives, it is good to kind of clean everything up before you go on to the next step. Derivative of this. We have a function raised to a power. So we bring the power in front, negative 1/2. Keep the inside the same. Subtract 1 from the exponent. And boom, we need the chain rule again. All right, and so now we can clean this up and we're done with the problem. So it's negative. So 2 times 1/2 is just 1. So it's negative 2x minus 1 to the negative 3/2. And we could do this many times if we wanted to. All right, so there's no reason why we need to stop at the second derivative. We could take the third, fourth, fifth derivative, and so forth. And so for the nth derivative, we use the following notation. So at some point, the number of primes is going to get out of hand. So we do y, and then we write parentheses n, like kind of as an exponent. That's saying the nth derivative of y. All right, similarly, we write f, and then, again, it looks like an exponent, parentheses n, that tells us the nth derivative. Or we could write dny over dx to the n, or we could write dn over dx to the n, f of x. So these are 4 different ways to write the nth derivative. So typically, we'll use primes for the first derivative, the second derivative, and the third derivative. After that, there's so many primes, might as well just use the parentheses. All right, so let's take a look at an example. And so why do we care about these higher derivatives? Each time we're talking about a rate of change. So like in physics, if you have some position function, you take its derivative, it tells you the rate of change of the position. That's called the velocity. And then if we take the derivative again, it tells us the rate of change of the velocity. That's what we call the acceleration. Okay, so taking multiple derivatives does have applications in some fields, and we'll see those. Okay, so let's find the first 4 derivatives of the function f of x equals 4x to the third plus 5x squared plus 3. All right, so pause the video and try this on your own. And then, yeah, let me know in the comments if you tried it. I don't think anybody will comment. OK, so let's find the first 4 derivatives. So we got to start with the first derivative and then work our way through. F prime of x is equal to, we bring the power in front, 12x squared plus 10x. Derivative of 3 is 0. F double prime of x is the derivative of what we just found. Bring the power in front, 24x plus 10. Third derivative. The derivative of 24x is 24. The derivative of 10 is 0. Fourth derivative. The derivative of any constant is 0. If I asked you to take the 100th derivative, it would be 0. The derivative of 0 is 0. So it would just be all the derivatives after this are 0. So it is possible at some point you find this pattern of all zeros. So just as the first derivative can be used to determine the rate of change of a function the second derivative which is f double prime of x can be used to determine the rate of change of the derivative. All right, so one way to interpret the second derivative is it tells us at what rate is our first derivative changing. All right, let's take a look at an example. So the millions of worldwide cellular subscribers, so basically the number of people that have some sort of cell phone subscription, can be modeled by the function c of t equals negative 0.895 t to the third plus 30.6 t squared plus 2.99 t plus 55.6, where t is number of years past 1995. All right, so when t equals 0, that corresponds to the year 1995. Right, so that's saying in 1995 there's 55.6 million cell phone users, cell phone subscribers. Cell phones were not nearly as popular in 1995 as they are today. In the year 5, we would get 2000, and so forth. Okay, so what I want us to do is let's find the rate of change of this function. Okay, so let's find the rate of change of our number of subscribers function. Okay, then we're going to find the rate of change of that function. Okay, so we'll find the rate of change of the function from a. And then we want to find where does the function from b equal 0 and interpret the meaning of that value. Okay, and so the rate of change, that's another word for the derivative. Right? The derivative gives the rate of change. So let's find the derivative of c, then we'll find the derivative of the derivative, and then we're going to set that equal to 0 and try to interpret what this means. Okay, so a and b, that's just derivatives. You're experts at that at this point. How do we interpret what it means for the second derivative to be 0? All right, so try this on your own, and I encourage you, let me know in the comments if you had an answer for C. You know, there's no shame in wrong answers. All right, so let's take a look at this. Let's first take the derivative. So we bring the power in front. So 3 times negative 0.895 is negative 2.685 t squared. Bring the power in front again, plus 61.2 t. And then the derivative of 2.99t is plus 2.99. And the derivative of 55.6 is 0. So we don't have to include that. All right, so this is the rate of change of the number of cell phone users worldwide. Okay, this is likely going to tell us that the number of users is increasing. All right, so part B, we want to find the rate of change of this function. So we need the derivative of this function, so that's c double prime, and that's negative 5.37t plus 61.2. All right, and we want to find when this is equal to 0. Right, that's for part C. So we want to set this equal to 0. And we solve. So this gives us that t is about 11.4. Okay, and now I'm going to show you how to interpret this. So what we should do is check, is our first derivative positive or negative around 11.4? Okay, and then we'll see what's happening with our second derivative. So note that when t is 11, so right before 11.4, our derivative is positive. So that means the number of subscribers is increasing, and the second derivative is positive. So the number of subscribers is increasing at an increasing rate. So each year it's increasing by more and more. When t equals 12, so just bigger than 11.4, the number of subscribers is still increasing. Right? Type this into our derivative function. It's still going to be positive. The number of cell phone subscribers is still increasing. But the second derivative is negative. This means it's increasing, but it's slowing down. Okay, we're not increasing by as much. We're starting to slow down. Right? Because a lot of people by the year 2007 had cell phone subscriptions already. So it's hard to keep increasing the number of cell phone subscriptions if people already had them. Okay? So how we interpret this is when t equals 11, the number of subscribers, speaking of the number of subscribers, you know what to do. So the number of subscribers is increasing at an increasing rate. The derivative is positive, so it's increasing. And the second derivative is positive, so the first derivative is increasing at an increasing rate. And when t equals 12, the number of subscribers is still increasing, but at a decreasing or slower rate. So the rate of growth is slowing down, but we're still growing. Okay? And so that's how you can interpret what the second derivative is saying about a function. So what do we do today? We saw the derivative of a function is still a function, so we could take its derivative, and there's a way to interpret what that second derivative means. Okay? So I hope you enjoyed today's lesson on higher order derivatives, and I will see you next time. Bye-bye.